Hello, and welcome to Introduction to Off-Grid System Sizing. My name is Gwendolee Espy. My background, a little bit about me, my background is electromechanical systems, and I'm an applications engineer here at Outback Power. Well, this webinar is intended for PV designers, so grid tie designers who are considering branching out to battery-based systems. We're going to be going over at a high level, a simple, basic off-grid system. This will assist with understanding basic battery-based system concepts and system sizing methodologies that should be helpful for you. We won't be covering a lot, all right? We won't be covering a lot of things in this webinar. Things like NEC code, string sizing, derating of PV and or batteries, environmental impacts on system design, site analysis, wind, module technologies, battery technologies, array orientation, conductor sizing, circuit breaker sizing, and more. We won't be covering a lot. This is just an introductory webinar. We're just going over basic concepts. All right, so this should be about a little bit less than an hour. So let's just get started. So like I said, this is intended as an introduction for grid tie installers that might be interested in battery-based systems. So some knowledge of electrical fundamentals like volts, amps, power, energy, watts, etc. is necessary for this webinar. Although, we will be starting with some basic design, like basic design concepts and considerations and nomenclature, and then we'll move on to a simple ball power calculation at the end. So training will assume an off-grid system, 100% battery backup. This will not contain all factors of system sizing. Remember, this is just a ballpark. This is just to teach the important concepts and emphasize the importance of energy and power. And at the end, we'll take some questions at the end. We'll only cover questions that are universal, questions that everybody would benefit from. We won't be going over specific questions of specific sites. Okay, so we will go over some definitions. So power is the rate. If you think of rate, so power is a rate of doing work. It's a rate of energy consumed in an electrical circuit. It is instantaneous energy. It's the flow of electrical charge. If you want to put it in an analogy, it's the miles per hour. It's the instantaneous speed, okay? Now, if we look at energy, energy is an ability. It's the ability to do work. It's charged particles stored in a source. It's the total of miles you're able to travel, all right? So it's the total miles you're able to travel. How far can you go? So here we have our analogy written out. So a rate is, for example, it's our speed. It's our instantaneous speed. It's miles per hour. And that equates to our watts. That's what watts is. It's instantaneous power. And then energy is the ability. So it's the total miles. So actually, if you were to do this exact calculation, your speed is your miles per hour times hours. That will get you miles, total miles traveled. That's the same thing as watt hours. All right, so watt hours is total energy. Sun hours, so the number of hours of full sunlight available to generate electricity. It's the amount of solar radiation or insolation delivered by the sun per day. In other words, it's the amount of energy by the sun per day. This will be useful when you decide how many modules you need, because the less sun you have in your area means you need to have more modules. And lastly is autonomy. Autonomy is the number of days a battery system can run with no sources, so no PV or other source. And that will be important in our system sizing. Okay, so our learning objectives. We're going to learn, why do we size a system? What do we size in a system? And how do we size a system? All right, so we're going to take a big picture look at the system, right? So the sun produces energy, and it delivers so much energy per second. Energy per second is your rate. It's your power. So we are capturing that with photovoltaics. So power over time is energy. Just like your speed over time will get you to a certain amount of miles, power will get you, over time will get you a certain amount of energy. So let's just continue on with some car analogies. Let's talk about this using gasoline as the analogy, okay? So if the sun produces power, over time, we can store that into energy or into batteries. Or you could instantly pass that power to the loads. So here we're collecting power, and we could either dump that in the battery, which we could store that as energy, so power over time is energy, or we could pass that on directly to the loads. There's a lot of components in here that we're not showing. This is just a simple illustration. So essentially, you can use that gas, right, to fill your tank for later use, or you can pass on that gasoline directly to your motor. So that's the analogy there. So what we will be talking about today is how to size your array so that you are collecting as much gas from the sun to fill your tank, and also how to size your tank so you're able to collect enough gas to also account for the evenings when you cannot collect solar power. And that's just to ensure that you don't run out of power each day, especially in the evenings. So gas in this analogy is power, and the gas tank is energy. So remember that your tank needs to be filled enough for your evenings too. So here are some things that are important that can make or break your system. And that is the accuracy of the solar data that you have in your area. Like I said, if you don't have a lot of sun in your area for super north, you're going to need more modules. And the second thing is the accuracy of the loads. And we'll emphasize this later, that having the accuracy, having that data, having that information that's accurate is going to be really important when you're sizing these systems. Too small, if you size your battery too small, you're going to drain or damage your batteries. And if you size your batteries too big, you're going to be spending too much money. Although you do want to oversize your system a certain percent due to losses and input-output fluctuations, loads, and solar conditions. So we'll go over a diagram later that will go over the importance of sizing more in depth. So this is what a basic off-grid system would look like. The top left, we have our PV. So this could be somewhere between 130 volts to 600 volts DC. It could even be beyond that as well, but generally we'll just say that. Next is the charge controller. So this is a DC to DC converter. Our PV will very likely be at a significant higher voltage than our batteries, which would normally be somewhere between 12 volts to 60 volts DC typically. So what the charge controller does is it steps down that voltage. So for example, let's say this array is a 300 volt array. So this charge controller would step down at 300 volts to a safe 48 volts. Let's assume this battery pack is 48 volts. And this is just making sure that the batteries can safely be charged. So the charge controller, we're moving on the charge controller here, the batteries, and the inverter all share the same point here, and that's called the DC bus. So electrons may flow freely from the charge controller to the battery, so it may go here or it could go directly to the inverter, depending on the loads and the state of charge of the batteries. So that energy or that power, that electricity that you're generating can flow either to the batteries or to the inverter, or in this case, our inverters also happen to charge our batteries as well, so it could flow back here. So this is our DC bus. Next, we have the inverter, which is a DC to AC converter. But like I said, our inverters are able to also charge our batteries, so it also is an AC to DC converter as well. And that outputs AC power to our subpanel, our DC to AC converter. So this inverter converts DC to AC generally. And that powers our loads essentially. And then also for backup, we can also have a generator in our system to provide power to the loads and or charge the batteries. That's just optional. Okay, so when we size, what do we have to size? So we're going to be talking about kilowatts. Remember, that's power. It's instantaneous. It's the rate. It's a rate of energy. And kilowatt hours, which is energy. It's the ability to provide power. All right, so we'll start with the inverter. So we're sizing the inverter for power. So how much loads are you trying to run all at one time? What's your worst case scenario? So the array in this case has little bearing on the size of inverter or an off-grid system. This is purely from your loads. What will be your loads? What's your worst case? Next is the solar array. So this is sized based on energy. It's based on energy consumed in one day by the loads. And this includes day and night loads. So solar array sized by energy. All right, next is the batteries. The batteries are sized based also from energy. This is your gas tank. It will tell you how many miles you'll be able to go. And then last is the charge controller. So the charge controller is sized based off power. And you'll see the calculations later. But so this charge controller, remember, it's in between the PV array and the battery. So you've already sized the PV array and the batteries based on energy. So now you need to make sure that the charge controller can pass through that power from the PV to be able to fully charge the batteries. Most charge controllers have a power limitation, so be aware of the maximum power your PV array can produce and ensure your charge controller is rated appropriately. So we'll be sizing this based on power, but this does directly affect the amount of energy you can pass through the battery from the PV array to the batteries over time. Okay, so we're going to be sizing all of these components. But remember, we're just going to be doing this in a simple ballpark estimate type of calculation. So first, however, we're going to go over why sizing these components are very important. We're going to focus on these three components, the inverter, the solar array, and the batteries for the next demonstration. And this will demonstrate why sizing is very important. All right, so here is a generic representation of a PV system in one day. So the lines represents instantaneous power at a given time in a day, whether that's from solar or whether that's from the loads. All right, so the bell curve in the middle represents the solar harvest here. So this represents a solar harvest in a day. The second line here, the black line, represents the electrical load demand throughout the day. In this diagram, you're able to see the maximum instantaneous power is indicated. So that's sometime in the evening. So this might be, like I said, this might be in the evening when the lights are on, you have the TV on, the heaters, computers are all running at the same time, everybody's home. This could be your worst case scenario, and this is what your inverter is sized for. So the inverter needs to be sized to be able to push out enough power for that worst case. Remember, inverters are sized for power. So the area, so remember, these lines represent instantaneous power over time, okay? But the area under the curve represents energy, total energy, so power over time. The bell curve in the middle, like I said, represents our solar harvest in a day. The area underneath the black line, so you have this black line, you see that gray, is a total energy required by the loads. Now notice that the yellow section here is the solar harvest that went directly to the loads. The red and orange color you see here underneath the solar harvest is the excess, and that excess is being stored in a battery. The gray is the electrical load demand that is not within the solar harvest, so you would normally be buying this from the grid. However, remember, in this example, we have batteries, and we're off grid. We don't have a grid. So let's see what this should really look like. So those batteries would be providing all of the load when the sun is down, or when the PV can't harvest enough instantaneous power to supply to the loads. Since we're not connected to the grid, the PV and battery sizing must be enough to provide the loads until the next solar harvest. So if you were to undersize your PV array, so say you undersize it so that it doesn't fully charge the batteries, then you would run out of power and you would have an outage until the morning or afternoon. If you design the PV without any buffer, and let's say there's a cloudy day and you could also run out of power, you could also run into this situation. So make sure you're designing to the worst case. So if you were to undersize your batteries as well, not only the PV array, but if you were also to undersize your battery bank, you could also run out of power and have an outage until the morning or afternoon. So it's really important to size your array and then your energy storage and make sure that you're sizing them appropriately between the two. All right, so let's say that you did design everything properly, but the end user adds some type of load you weren't expecting. It's shown here that that load got turned on in the evening. Then your design system wouldn't be sufficient to support the additional loads, right? So here, let's look back. So this is normally what you designed for, and they had some extra load on in the evening. So essentially, what would happen is you would run out, right? So you would run out prematurely, and you wouldn't have any power until the following solar harvest. So this is why it's really important to understand the loads and any future loads that have, and to be able to have that conversation with the end user and really understand what are they planning to do. And also make them understand what the consequences could be if they weren't really explaining their needs, or if they were to add something that you weren't expecting. All right, so this diagram shows adding some type of buffer. So adding some design factor or buffer will account for fluctuation in loads or weather. We're going to call this adding extended energy storage. So the red, what you see here, is what you live on every day. So this is what you're designed. This is what you would expect. The faded red, you see bordering it, is the extended daily energy, or it's your buffer. So this is stored in the battery. One way you can think about it is that the top line is, this top line here, is the extra capacity you have that can be used at any time. Because we have batteries, we can shift this extra energy anywhere and anytime that we want. And this represents, this design would represent additional PV and additional energy storage combination. So that's really important. You need to make sure that you upsize both your PV and your batteries. So let's say that there was an additional load in the evening that you didn't count for. That buffer could provide enough energy for that unaccounted load. So we will be going over how do we size. We're going to size these 4 components, and we're going to go over it in a simplified ballpark estimation method. So there are more complicated calculations within many of these steps. I want to emphasize that. There's way more that we're not going to cover, but we will not go into that much into that detail. We are calculating the system requirements at an introductory and a high level. Okay, I just want to emphasize that. We're not covering everything. All right, so how do we size a system? Well, we're going to calculate the total loads and energy per day, and this includes the maximum power needed. So remember, this is the, let me go back. This is this number. What is our worst case scenario? What would be on all at the same time? All right, next we would be calculating our losses and efficiency. Then calculate the days of autonomy, or decide on the days of autonomy. Size the battery bank. Calculate the sun hours in your area. We won't be really covering this. We're going to be assuming that we are in Phoenix. Already did that calculation for us. Then we're going to size the array and size the charge controller. I believe in learning and repetition, so we will go over these concepts each. So we're going to go over the concepts first, and then we're going to go over again with an example. So there is a big difference between a grid-tie system and a battery-based system. Okay, so unlike battery-less tied grid systems, you must account for power as well as energy. So that not only power is important, but energy is important too. So remember, power is instantaneous. It's measured in watts or kilowatts. It's your miles per hour. And energy is measured in watt hours, or it can be measured also in amp hours. It's power over time. So it's our miles per hour. It's our speed times hours. So there are three methods for quantifying loads. The first method is measuring. So when you get your power bill, it should really be called your energy bill because it's power over time. And this is actually very useful for battery-based inverter design. This uses actual data and actual usage history. This is the best way to get your load calculations. The second way is to calculate it. So this is used for new construction as they normally don't have any data. So this is the second best method to get that information. And the third, which I don't recommend at all, is guessing. And it can be the most common method and is completely unreliable. I do not recommend it. I'd recommend either measuring, which is the best method, or calculating. So I've gotten this question before. Hey, I have a 2,000 square foot home. What size system do I need? That gives me almost zero information. Let me put it this way. It's like asking, hey, I just bought an average car. How much gas will I need to buy this year? What would you say? Well, you'd say, well, it depends. You'd probably ask them a lot of follow-up questions. What's your usage? What car do you have? How do you drive? What's your commute like every day? Do you do a lot of road trips? So you really can't determine anything without more details. Square footage, there's no correlation between square footage and solar. It's useful for other things like carpeting or paint, but when it comes to system sizing, especially off-grid system sizing, we need to deal with loads. So it's really, this step one is critical. No electrical or electronic component is 100% efficient. Electronics will, when they run for a while, they heat up, right? And heat is energy. So that's losses. That's energy you're not putting directly to your loads. It's just going into the environment. So you may start with 1,000 watts at the modules, but you might end up with actually 850 watts available to your loads. So you'll have to account for this in your calculation. So if you need 1,000 watts at the loads, you'll need to probably harvest more than that at the module. Listed here are possible or typical efficiencies of solar components. When you actually do a design, you should be looking at the manufacturer literature on each of the components to get the actual efficiencies. So a charge controller could have 97, 98% efficiency. Batteries could be 90%. Inverter, 90 to 93%. Conductors, 96 to 99%. For our calculation, we're going to assume the best case scenario. So we're going to assume we looked at each spec sheet. We found our charge controllers at 98%. We chose batteries that are 90%, inverter that is 93%, and we're going to assume their conductors are 99%. So when you multiply all of these percentages together, we're going to end up with 81% system efficiency for our calculations. And that, although we don't have the inverter in here or the charge controller, but that's efficiency from the panel out to our loads. So that's our total efficiency, 81%. We will be using the inverter efficiency, 93% for our batteries, and I'll explain later. Days of autonomy. So sometimes the sun doesn't come out. Well, not completely. It could be a cloudy day, or perhaps a storm passed through, left some leaves on your panels, or it's snowy. there's some snow on your modules and you're not able to get to it for half the day. For whatever reason, you might not be harvesting enough during the day to replenish your batteries back to 100%. So you may run out of juice in the evening. To account for this, for like these possible occurrences, you may want enough energy storage for multiple days. So we have an off-grid application. So as a designer, for whatever reason, we spoke with our customer, we understood their application, and we decided, okay, we're gonna do 2 days of autonomy with this customer. So we're gonna be using 2 days. All right, so now we are going to size the battery bank. So we have a total energy from our step 1 from our load calculation. So we did this by estimating what loads power requirements are, what the requirements are, and how long they are on for in a particular day. Remember, energy is in watt hours or amp hours. There will be some efficiency loss in the system, so the batteries will need a little more energy than the loads require, since some of it will be lost through heat along the way. So we're going to choose the inverter with 93% efficiency. And let me explain why we're using 93% and not our 81%. Let's go back up to our diagram. Okay, so from the battery, so the path from the batteries to the loads, you started your battery, you go through your conductors. So I guess we could possibly include our conductors too, but hopefully that's a short enough distance between your batteries and your inverter. So you would go from your batteries through your inverter to your loads. So remember, the PV array has to go through lots of conductors, your charge controller, maybe into your batteries and back out of your batteries, possibly, and then to your inverter. So that's kind of the worst case, is your 81%. But when you're dealing with your battery efficiency, the battery is really just output through your inverter to your loads. So when we size our batteries, we're just going to be using our inverter efficiency because that's the normal path. Okay. Let's go back. Okay, so system designs with lead acid batteries typically only discharge the batteries around 50%. Normally, discharging lead acid batteries more than 80% is not recommended. You could discharge as much as you want, but there's some trade-offs between percent discharge and battery life. Battery manufacturers provide literature on that trade-off, so designers can make that decision on what percent they want to discharge the batteries for what their application is. And even some manufacturers, you have to be really read the literature closely, because some manufacturers have a requirement for maximum depth of discharge with their warranty. So really know what the literature says for the batteries you decide on. Some off-grid designers have larger battery banks so that they only discharge 30% of the batteries with intention to extend the battery life. There are other technologies such as lithium ion that has the capabilities to discharge 100%, but there are some trade-offs with that, such as initial cost and complexity. So we need to consider also our 2 days of autonomy. So that means that we'll need twice the batteries. So that's something also to consider when you think about the days of autonomy that you want, because the cost of that could increase significantly. So here we have our equation. We have our amp hours, and I'll explain how we get that. So we have our total energy divided by our 93%, so that's our efficiency. Our depth of discharge is our 50%. We're going to move forward with that. We have our nominal battery voltage. So to go from watts, so watts is equal to current, which is amps, times voltage. Watts is equal to current times voltage. So in order to get current, right, you divide your watts by voltage. So that's what we're doing here. Our total energy is in watt hours. We're dividing it by our nominal battery voltage to get amp hours. And that's how we get our amp hour rating. Okay, so the amount of solar modules will depend on many factors. One being how much energy from the sun is available at that location. If there's less sun, you'll need more modules to make up for it. So there's data and websites available to search for the minimum, average, and maximum sun hours for an area. Winter solstice, which is at the end of December, is typically the worst case and the most conservative value that you would get. The sun is very low on the horizon, and it's the shortest day of the year. Well, since this is an off-grid home and we are expecting it to be occupied all year, we will use the most conservative value. So I already did the research. So we're in Phoenix, and our value lowest installation would be 5.78 sun hours. I just want to note, however, it really just depends on the application which value you should use. So if you knew the home would never be used in the winter and only in the summer, perhaps using that winter solstice data would not make sense. You might be oversizing the system for its intended use if it's only being used during the summer. So you would just need to make sure that your solar array was sized enough to keep the batteries at float so that they don't go bad, but you might not need to size your battery bank of solar as much if that was the application. So that's just something to note. And finally, the minimum size of the array. So like I mentioned before, the amount of solar modules and configuration will depend on many factors. We will not go over many of those factors. We're just doing a ballpark, okay? So this section is a lot more complicated than what we're doing. We're just doing a ballpark. So at this time, we have estimated the total daily energy usage. We have our sun hours, and then for the location, and we have our estimated efficiency. So this will give us the minimum PV watts that we need. So this will give us watts. We have our total energy that we calculated from our step 1. Then we have our system efficiency, and then our sun hours. Oh, charge controllers. So last is our charge controller. So remember, a charge controller is our DC to DC converter. The PV voltage, the array voltage, is probably going to be a lot higher than your battery voltage. So that's why this charge controller comes in quite handy. So this steps down that high voltage down to a safe level so it can charge your batteries properly. When you do size a charge controller, you have to be aware of the power rating of the charge controller. You have to make sure that that charge controller can pass that power from your array to your batteries. It's not going to limit that. And then you have to consider the number of charge controllers you might need and the PV configuration for each charge controller, which we will not cover. All right, so we are now going to do an example calculation. We're going to start with step 1, calculating our loads. So we're going to determine the maximum instantaneous power that we need and the total amount of daily energy. So this is no different than what you may have already done in the past, but now it's very critical to get it right for an off-grid system. So you got to know the loads that are in the system, how long it's expected to run, and which scenario will produce the maximum power. So which loads would be on all at the same time. So here we have a house which is powering 2 heaters, a TV, and 10 light bulbs. So here we have our quantity. We have our 10 light bulbs, each are 15 watts. That would give us a total 150 watts. We know that the light bulbs will be on for 8 hours a day, and that gives us 1,200 watt hours per day. The next we have a television, 1 television. We know that the television is about 100 watts. We calculate that to be a total of 100 watts. And then we know it's running for 4 hours a day, which would give us 400 watt hours per day. And then last is our heaters. We have 2 heaters, each at 1,500 watts. That gives us a total of 3,000 watts. We know that the heaters will be running 4 hours a day, and that gives us 12,000 watt hours per day. So, all right, so here we have our maximum power. So we add up our total watts here. This will be our maximum power. And the next slide I'll describe to you that we do expect all of these loads to be on at the same time. So this will be our number that we're working with. This is our worst case scenario. And then finally, our daily energy. So we add up our daily energy, we get 13,600 watt hours. So this is the energy that we will have. It is possible that, let's say that you know that only one heater will be on at a time. So you might not be considering that for your worst case because you know there's no way that both heaters would be on at the same time. So you might not you might not need to have that as part of your calculation. So you really need to know which loads will be on all at the same time and which is your worst case. So what we're looking at is a clock. So this clock is from 12 p.m. It's 12 p.m. to midnight. We know that we had our conversation with our customer and user. We know that this is when they use the loads. Okay, this is when the loads are on. From our research, the TV is on for 4 hours, the light is on for 8 hours, and the heater is on for 4 hours. There is a time, so I have these are when the loads are on. So the heater's on at this time, the TV is on between 3 and 6:30, and then the lights are on between, 4 to almost midnight. Okay, so talking to the end user, we do know that there is an overlap when all of the loads will be on at the same time. So we know that that's going to be our worst case scenario. And then also, we also know that the batteries will be discharged over 12 hours a day. So for whatever reason, the end users are using 0 loads between 12 a.m. to 12 p.m. So in the mornings, they're not using any loads. That will come in handy when we size the batteries. So understanding, will we need this energy over a short amount of time or will we need this energy over a long period of time? Because how fast lead acid batteries are discharged will affect your battery capacity, and we'll go over that later. You know, the real world scenario won't be so easy because I got to control all of the variables. This is a little bit easier for me. It really just depends on the customer and understanding your customer and really understanding what the worst case would be. Okay, so remember, this is our calculation. We're going to be pulling this max power and daily energy and to do all of our calculations. So here it is. Step 1. So we're still sizing our loads or understanding what our loads are. So step 1 is the last part of a load calculation. So we know our maximum power is 3,250 watts. So we need an inverter that can handle 3,250 watts. So with the VFXR 3648, it's able to do 3,600 watts continuously. We're good. We're going to move forward with that inverter. As a designer, you'll need to do the research on how efficient your components are that you choose and make sure that you get the correct system efficiency. We won't do these calculations. We kind of did a little bit earlier, but we're going to assume our 81% efficiency. And then we kind of already went days of autonomy as well. Remember, days of autonomy is in reference with the number of days a battery system can run with no PV or other source. So for our purposes, remember, we spoke to our customer, we understood their application, their budget, and we're going to go with 2 days of autonomy. And remember that this can add up really quickly if you were to continue to add more and more days of autonomy. So be aware of your customer's budget. Now we will size the battery bank. So we have total energy from our load calculation. There will be some efficiency loss in the system, so batteries will need a little more energy than the loads, since some of it will be lost through heat along the way. So lead acid batteries typically have 50% capacity available. I mean, they have really more than that, but then you're affecting the life of the battery. So we're going to move forward with 50% depth of discharge. Remember, typically discharging lead acid batteries more than 80% is not recommended. So we also need to consider our days of autonomy. 2 days means twice the amount of batteries. And then finally, remember our voltage. We have our nominal battery voltage. Watts divided by voltage is equal to amps, and that's how we get our amp hour here. So by doing this, we did our calculation. We have our total energy divided by our inverter efficiency, our depth of discharge, our nominal battery voltage times 2 days. We get 1,218 amp hours. So that's the total, that's our minimum battery size that we need. All right, so we're gonna take a side step. All right, we're gonna take a side note. I won't go over this in very much detail, but we're gonna talk about this for a little bit. So like I said, how fast you discharge your lead acid batteries will affect the capacity of your batteries. So what we need to look at is the hour discharge capacity. Understand how many hours are we discharging this battery and what capacity will we have that relates to that hours, okay? You might have heard this before as C rates, but C rates have to do with, mostly it has to do with charging current. It has to do with a rate. It has to do with current. So you may have heard this as C rates, but we're gonna call it hours discharge capacity. Or you might see in some of our spec sheets is discharge in hours. Okay, so we're gonna get this number, all right? How many hours are we discharging this battery? So the hours discharge capacity is the capacity that a battery has if it were to be 100% discharged over an X amount of hours. So we're gonna calculate those hours. This is not the example that we're doing. This is an extra example that we're doing. Then we're gonna do this again with our actual example. Okay, so remember that the hour discharge capacity is the capacity that a battery has if it were to be 100% discharged over an X amount of hours. So here we have our battery sizing, okay? So we have our hours discharged per day times days of autonomy divided by discharge per day, percent discharge per day. So this is our depth of discharge. So here we have our battery bank, okay? In this scenario, we are discharging the batteries over 24 hours per day, okay? We size this battery bank, and we have 2 days of autonomy. So what that means is that we're discharging 24 hours, and then we're discharging another 24 hours, 2 days. At this point, we're not discharging our batteries anymore. So this is our 50% depth of discharge. This is what we decided to discharge our batteries to. If you had decided to discharge them 80%, this would look a little bit different. Our calculation would be the same, but the diagram would look different. Okay, so we decided to do 50% depth of discharge. But remember that our hours discharge capacity is the capacity that a battery has if it were to be 100% discharged over an X amount of hours. So if we were to discharge this battery to theoretically, we would never do this, but theoretically, 100%, we would be discharging this battery a total of 96 hours. So for our application, because of these variables, our hours discharged per day, our days of autonomy, and percent discharge per day, we will end up with a 96-hour capacity, okay? We're gonna do this one more time with our actual scenario. So remember that clock we had? We know we're only discharging our batteries 12 hours in one day. So they're hours discharged per day. We know that we decided to move forward with 2 days of autonomy, and we're only discharging 50% discharge. This is your percent depth of discharge, okay? So we have 50%, we decided 50% depth of discharge. So this hours discharging per day would be 12 hours, days of autonomy would be 2, and then percent depth of discharge would be 50%. Okay, so we have our 12 hours, and then we have another 12 hours. This is our first day of autonomy, or first day, and then our second day. So we know at the end of this, we're going to be at 50% depth of discharge. But remember that our discharge capacity, what you may have called C rates in the past, our discharge capacity is dependent on 100% discharged over an X amount of hours. We're trying to get, what's that X amount of hours? So if we were to theoretically discharge this battery 100%, this would be over 12 plus 12 plus 12 plus 12. So at this point, we would be at or at 100% at the discharge. We would be discharging this battery for 48 hours. So we would be using the 48 hours, so discharged in 48 hours number, okay? So that's what we're going to be moving forward with. So this is actually our example because we're discharging our batteries 12 hours in one day. So we're going to be using our 48-hour capacity. Hopefully that wasn't too confusing. All right. So we know that we need batteries that are 1,218 amp hours that are at the 48-hour capacity. And we know that our batteries are 48 volts. So that's the system size that we decided was 48 volts. So we're going to look at our battery options, and we saw that, hey, the 1300 REs has a capacity of 1,269 amp hours at the 40-hour capacity. So that works for us. So we're going to move forward with that number. So 1,269 amp hours. Generally, some people use the 20-hour number, or they might use the 24-hour number when it comes to depending on their days of autonomy, and that's fine. It's a lot more conservative. Remember, the higher this number is, the more capacity you have, because the faster you discharge your battery. So this is assuming you're discharging 100% of your batteries in 48 hours. If you were to discharge your batteries in 24 hours, you're going to have less capacity. So you could use, the 24 number or the 20 number. It's just going to be more conservative. But if you wanted to use the right number, you could use the calculation. And remember, this is depth of discharge, percent depth of discharge. So that would be your 50% in both these cases. All right, then we have our calculating our sun hours. So we won't go over how we got this number. Like I said, there are websites to show you how to do this. So we have 5.78 sun hours for our location. All right, so now we're going to size the array. Okay, I want to emphasize, again, the sizing the array and the configuration of the array is more complicated than what we are doing here. Okay, so there are angles and spacing and temperature and much more that needs to be considered when finalizing the design and the configuration of the array. So what we're doing here is just a start. It's just a ballpark. So the minimum PV watts can be calculated by dividing the total amount of energy. So we got this number from our original calculation. Everything kind of stems from step one here. That kind of emphasizes how important getting your load information is. So we have our 13,600 watts. We're going to divide that by our system efficiency of 81%. And then also by the sun hours that we would have gotten from our website. So in our case, it's 5.78 sun hours. And by doing this, we get 2,905 watts. So this is the minimum amount of power we need from the PV modules. So let's see how many modules we need to meet this requirement. But first, remember, we sized this based off of energy, and we happen to get power. And then this is what the charge controller power rating comes from. But we'll talk about that a little bit later. All right, so we're going to see how many modules do we need. Let's say we already have a large stock of 320 watt modules. So, and we would like to use that stock. So we're going to move forward with those 320 watts modules. So we know that our minimum wattage is 2,905 watts. And we know that each of the modules is 320 watts. So if we divide those two, so 2,905 watts divided by 320 watts, we get 9.08 modules. Well, we can't have 0.08 of a module, so we're going to have to make a decision. We're going to have to decide if we want to round up or round down. And this is really up to the designer. So if you want to round down or up. We're going to round up. Some might want to round down. Let's say that you already added like a significant buffer, and I'll talk a little bit about that later. If you already added like a significant buffer in your system design, maybe, you know, that 0.08 wouldn't really affect anything, but we didn't. And maybe we should have, but we didn't. So we're going to go with 10 modules. So 10 modules at 320 watts, that's going to get us 3,200 watts total at our array, which is above our minimum of 2,905 watts, so we're good. Okay, so this is for my grid tie installers. I said earlier that we're not going to go into a module configuration, but I will say this. So for most 80 amp, 150 volt charge controllers, you might just round up to 12 modules. You know, so you might go for a 4x3 configuration because you might think, hey, 10 modules, that's kind of an awkward number. However, with our FM100, which is a 100 amp, 300 volt charge controller, you could actually do, because you have your 300 volt charge controller, you could actually do 2 strings of 5 or 2 strings of 6 or 2 strings of 7 in series with this charge controller. But really, it's whatever is best for your design. So we're going to go with the 10 modules. Okay, so last we're going to size our charge controller. So we are actually going to be sizing this for power. So this stemmed from our array sizing, which originally came from energy, but we now have our PV power. So we know the power the PV could produce is 3,200 watts. So we want to make sure that our charge controller can pass that on. So can just pass that power from the array to the batteries. So we want to make sure we have a charge controller that can handle the 3,200 watts. Well, the FM100 can handle at least 5,000 watts. So we're going to move forward with the FM100 because it's 300 volt VOC. We can do 10 modules with 2 strings, and 5 modules in series. And this is assuming these modules are I think they're about 40.2 VOC. So we can do that and still be under 300 volts. All right, do you remember when I mentioned buffer a few slides ago? Well, I want to note that we did all of this with no buffer, okay? We did kind of, you know, add a little bit of buffer. So when we had a buffer when we, you know, upsized a little bit on our energy storage, and when we upsized a little bit in our PV array because we had to go with 10. So inherently we did add a little bit of a buffer, but really it's really smart to just add a buffer from the beginning. All right, so let's see. So, you know, when we add additional energy storage as backup, once you get your solar fully back and fully functioning, the end user will need to decrease their loads to allow the PV modules to replenish 2 days worth of energy over a few days. So this is just a note, you know, if your power went out and you oversize your batteries, you have to allow that time for the batteries to become recharged. So you might have to control your loads during that recovery time. You can add like additional PV, so slightly oversize your array in reference to, or that's in relationship with your battery. And that's just to maybe more quickly charge your batteries. Once your batteries are charged, though, you might not be utilizing. So normally this would come up and back down. So you might not be using that power anymore because your batteries are full, etc. So that's a possibility. So you might not be fully using your array at all times, but you could be charging your batteries much faster. Okay, so buffering. So if you do you want to add a buffer? You would do that here at step 1. Okay, so you would add some type of, you know, you can add a 20% buffer. You'd probably just do that for your daily energy. You could add a 20% buffer, 10% buffer, whatever is appropriate for the area. If you suspect that your end user might add some loads, you could also add a certain buffer there as well. Actually, you know what? Just to point out, notice we didn't really We only used the max power for the inverter. Everything else came from the daily energy. So really sizing your energy is so important. Okay, let's go back. All right, so if you do want to add your buffer, like I said, adding a percent to step 1 is how you would do that. All right, so now we have calculated and sized all of the components, and it all stemmed from knowing the loads, both maximum power and daily energy, not square footage, not square footage. We have sized the inverter for power, okay? So we had, we needed at least 3,250 watts. We calculated that. Remember, having that energy bill, though, if it's an existing site, way more valuable than calculating it. So with a VFXR, it can provide 3,600 watts, so we're going to move forward with that inverter. Batteries, so batteries we have sized for energy, and it's your gas tank. So we needed at least 1,218 amp hours. And with the RE1300, we got 1,269 amp hours. So this is kind of what I'm talking about. We added a little bit of buffer when we had to round it a little bit up with when deciding what components we wanted. Solar modules, so we size the PV based on energy. So we need to know how much energy do we need to put back in the batteries in the short amount of time when the sun is out. Those are your solar hours. So we needed 2,905 watt array, and we went forward with a 3,200 watt array to meet that requirement. And since we have 3,200 watts available to us in our array, we want to make sure we're able to pass that power directly to the batteries. Otherwise, we might not be utilizing all of that power. So with the FM100, we're able to do at least 5,000 watts, so we have no problem. We can pass that 3,200 watts directly to the battery. So that's pretty much it. We did that ballpark, and like I said, there's so much more to this. I mean, I wouldn't actually choose components based off of this. This is more to kind of understand, what are you sizing, why is it important? And like I said earlier, for the inverter was the only thing we used power for. Everything else was based off energy. It's so important to understand your loads and how long your loads are for. All right, questions? I just want to say, though, my name is Gwendoline Espy, and thank you so much for joining us, and I hope you found this valuable. Thank you.